Let us now move on to our third session of the day, which is on emerging technologies. I would invite Dr. Jay Asundi, Executive Director at the CSTEP, who will be chairing the session, and the guest speakers, Professor T. Rajkumar, Head of Department of Molecular Oncology at the Cancer Institute, Chennai, and Dr. Nandan Sudarsanam, Associate Professor at IIT Madras.
Good afternoon. I hope everyone's feeling, I think we can settle down. I hope everyone's feeling good after a nice lunch. I hope that also means that we've set up a couple of talks for you on technology, and I'm sure that you will learn a lot, so will I. Our first speaker is Professor T. Rajkumar, who's Professor at Department of Molecular Oncology at the Cancer Institute in Madras. He has a PhD from Hammersmith Hospital, London, UK, and he has a degree in medicine from the Madras Medical College, and also did a medical oncology from the Cancer Institute, where he is currently faculty. He's the first qualified medical oncologist with a PhD in basic science, and he's also the first clinical oncologist to be awarded the DSc by the thesis in India. Without further ado, let me call upon Professor Rajkumar to give a little brief on issues around immunology, public health, and biotechnology. As many of you would have seen, the whole COVID pandemic and our interest in biology has increased more. I think this would be a really interesting insight into this subject, and maybe issues around what you need to think about as you start exploring this particular subject. So, please, sir.
Good afternoon, everyone. At the outset, I'd like to thank Dr. Nalini for giving me this opportunity to be present amongst you. This is frankly a new experience for me to be interacting with journalists and future journalists. I also thank Dr. Nalini to giving me this opportunity, because I find my senior from my school here, Dr. Sasikumar, I'm seeing him after ages. It's so great to see him and see you all. So what I plan to do maybe in the first 20 minutes is to just run over some of the developments based on what you had put down, immunology, molecular biology, and the societal impact, and then maybe have a much larger discussion after that. So first, talking about immunology. So basically, in very simplistic terms, immunology refers to the field which delves on the immune system, the way it protects us, the way it can even harm us. So this is the thing this is the system which is necessary for us to ward off infection, ward off tumors, etc. So it has a major role to play in us. So I just put down these two pictures here. What you see on the top is the COVID pandemic and the number of deaths which we had. It's enormous. And the other one is, sorry. So the other one is a film, The War of the Worlds, where he had an alien invasion of the Earth. And you find that there is a commonality between the two. The first thing is lack of immunity is the reason why we had so many people being infected and large numbers also having died, because we did not have an immunity, or our immune system did not see the virus, the COVID virus, when it came about. And that is the reason why we had the whole lockdown, everything coming in. But over the next year or 2 years, we were able to develop newer methods to fight the infection. Now, coming to the War of the Worlds, again, the aliens did not have immunity to the infectious agents in the earth, and that is the reason why they died, and finally the earth won by default. So the immune system, therefore, is a very major component in ensuring that the human race survives better. Don't go into the details of this. This is just to tell you that the immune system is very complex. Biology is invariably complex. The immunity or immunology as such is, through its nature, is also complex. Simply put, every one of us has, when we are born, we have what is called as the innate immunity. This is what we are born with, the skin. Skin protects us from the external agent. So that is something, the skin, the lining in our mouth, the GI tract. So these are all protective agents. These are all innate immunity components. We also have cells which are there, which have not seen any bacteria, etc., or viruses, but still they can function. So these are called as the natural killer cells. So these are also part of this innate immunity, the cellular elements. And then you also have in the blood complement system, etc., which again help in beating back any viral or bacterial infection if it were to occur in a baby. And this is something which we normally see in the newborn developing some infection, or most of them are born and then fortunately they do not develop a problem, and you like to attribute all that to this innate immunity. The second component is adaptive immunity. COVID is a classical example of adaptive immunity. So this is something which we did not see, we did not know, the immune system did not know about it, but once we were exposed to it, the cells within the body were able to identify it and then trigger a response, and that is what was used for the vaccines. In the vaccines, they chose some of the proteins associated with the COVID virus, for example, and then immunize the people. So the logic was, if the immune system can see these proteins, then when the virus comes into the system, into that individual, they will have a much better chance of fighting it off. So that is the basic rationale. And adaptive immunity, therefore, essentially deals with the lymphocytes, the T lymphocytes, B lymphocytes, the antigen-presenting cells, etc. Let's not go into the details, but just understand that adaptive immunity is something which is acquired. It is not something which you are born with. So these are again cartoons to essentially tell you that the innate immunity and the adaptive immunity function in slightly different ways, because essentially you do not need initial priming for innate immunity, but for adaptive immunity you need the antigen presenting cells to present to the immune cells, the T cells, the B cells, etc., to destroy bacteria or a virus containing cell. So that is the importance. And these are again to emphasize that you have the development of these effector cells. Effector cells are those which are the ones which ultimately go and destroy the organism, bacterial organism, or a cell which has been infected with virus, and therefore it can be cleared out of the body faster. So this is just to tell you what happens if a viral infection were to occur. Let's presume that you have a virus here. This virus is made up of proteins, and the proteins for these viruses is actually coming off from its own genetic material. So it can be RNA, it can be DNA. Now, once the virus enters the body, the viral proteins get broken down. It's chewed up in a mechanism. This is our machinery in the cells. Every cell has this. This is called as proteosome. Its function is to break down the proteins. Even the normal physiologically, every day, every cell, even without any infection, the cell has to clear out things which it doesn't need. And proteosomes help in removing all those unwanted proteins basically. So that machinery comes in, it breaks down that viral protein into small bits, what we call as peptides. And these are then bound to what we call as the human leukocyte antigen or HLA molecule. I think some of you all would have heard about this. It's very important because Every cell, every nucleated cell, a living cell, has what we call it the HLA-1 or molecule. HLA-2 molecule is more restricted, but here every nucleated cell will have this. The reason it has to be there is because this viral peptide, the small portion, the protein which has been broken down into a small fragment, has to be exhibited on the surface of this HLA molecule on the cell surface. So it's a flag. It's telling the immune system, guys, I have something in me, it's not normal, please come. So that's a flag that would allow the T cells or the B cells or macrophages to come in and attack those cells, and if they've already seen it, they can destroy that entire cell. It's something which is, I'd say, necessity, because you don't want the viruses to spread to the neighboring cells. But if there is a situation where initially you have not seen the virus, like as in the COVID, you may have infection for a period of time, but within that period, the body's immune system will start seeing this as being foreign and then start destroying it. One of the important person, at least in my undergraduate days in MBBS, whom I found very fascinating, was Burnett. Now, he proposed a theory of immunosurveillance. Every one of us, at any given point of time, have cell divisions happening within our body. These cell divisions can be in the bone marrow, because we need to replenish the red blood cells, which have a lifespan of 120 days, the neutrophils, which have a lifespan of less than 7 days, etc. So there is a continuous need for these to be replenished. So divisions are required, cell divisions are required. The entire skin, you'll find that it gets shed off, and they have to be replaced. So much of cell division happens. When such an amount of cell division happens, you are always a possibility that some of these cell divisions can go wrong. And when it goes wrong, you can have a potential for a tumor to develop. Burnett's hypothesis was that if the T cells within the body can actually be like a policeman patrolling the entire body around and identifying any hallmarks for these tumors at a very early stage. And if they do detect it, they destroy those cells. So as I speak, even I would be having tumor developing and being destroyed. So this is a vital function, and this has been subsequently been shown to be true as well. So this is basically what was mentioned, I was mentioning. So you have the tumor cells growing out, and when the tumor cell is being generated, it's an abnormal cell. Please understand that the tumor is not a foreign cell. It's basically our own cell which has changed its behavior. And when it has changed its behavior, a lot of things happen. It can secrete new proteins, etc. The DNA which it contains can be released, as a result of which these can trigger the immune response. And finally, that can lead to the death of the cell. So that's basically the mechanism by which the tumor cell kill happens. When you have something as potent as this, sometimes, why is it then we develop tumors? There are people who develop cancers. Cancer has become #1 killer now in the country. And the reason is the cancers are becoming smarter. They try to evade the immune system. Normally, you would have what is called as an immunogenic cell death. At the immunogenic cell death, there is a lot of materials coming out of the cell, so which can actually stimulate the immune system, so that they can then, the immune system gets triggered, it gets amplified, you can then wipe out that tumor which is developing. On the other hand, sometimes you can have what is called as tolerogenic death. The cell dies, the cancer cell dies, but it does not release some of these components, and therefore the immune system is actually unable to see that there was something abnormal here. So there is no response mounted in that situation. It's like a person who has got into a city, or let's say a terrorist who has gone into the city and it's been completely difficult to identify. Now, at any given point, there is a battle in the tumor. This is a well-developed tumor which you see here. The tumor cells are surrounded by what we call as tumor microenvironment. And this consists of a variety of cells. Some of these cells are trying to protect, prevent the tumor from growing or help to destroy it. On the other hand, you have elements which can promote the tumor to grow more. So both these are happening. At the end of the day, whether the tumor is going to grow or not will depend upon when side the balance tilts. And immunosuppression in the tumor microenvironment is one of the critical factors. And that is one of the reasons why newer therapies have come about, which we'll talk about a little later. So here, these are, again, don't go into the details, but just to indicate that now one of the important things which people have called as the hallmark for cancer is this avoiding or the tumors having the capacity to evade the immune system. And that is one mechanism which is required to say that possibly is a tumor there. Now I'm moving from immunology to immunotherapy. Why am I doing that? Primarily because as journalists, you'd like to know what is the newer developments which have happened here. And we could classify the immunotherapy into cellular and non-cellular immunotherapies. Non-cellular immunotherapies, I think some of you all would have heard about monoclonal antibodies, which are targeting specific proteins on the surface of the tumor cells. So this is something which has been there now for more than 23, 24 years. So rituximab was one of the first monoclonal antibody which was used to treat a form of cancer called as lymphomas, B-cell lymphomas. Then you have more recently monoclonal antibodies, but these are called as immune checkpoint inhibitors. I'll talk about that in a short while. You can also have vaccines, cancer antigen vaccines. People have tried all this, where they take the patient's tumor, prepare a lysate or something, and then give it back as a vaccine, small doses. And then you also have proteins which are being secreted either by the immune system to promote the cell destruction. BCG, which I think most of you all, at least those who are in the middle age, would have had this vaccine as a protective agent against tuberculosis. It's used as a therapeutic entity for bladder cancer, early bladder cancer. And then we also have several new pharmaceutical drugs which are coming into this to modulate the immune response. On the other hand, you have also cellular forms of immunotherapy. Now, the most important one of interest is the CAR T cells. So we'll see that in a while. So here we have the monoclonal antibodies. So the idea is that monoclonal antibodies have two arms which would bind to a particular protein on the surface of a tumor cell. And they can then bring about cell destruction by different mechanisms. Don't worry about the mechanisms. So, but the basic bottom line is monoclonal antibodies are a very good armamentarium for treating cancers. The cost initially was very high, but with generic monoclonal antibodies being available, it has come down. But I wouldn't say that they are still cheap. And now you have a whole lot of cancers which can be treated with monoclonal antibodies. The most important one at this point of time is breast cancer. In breast cancer, there is a protein called as HER2 protein. The HER2 protein is overexpressed in about 20 to 25% of breast cancer patients. And when it is overexpressed, it is present on the surface of these cancer cells all along. And there are monoclonal antibodies which have been developed which can target that protein and destroy the cell. And it's therefore a very important development in breast cancer management. Now, next is the immune checkpoint inhibitors. First of all, why do you need an immune checkpoint at all? On the one hand, you have an immune system which is necessary to destroy a foreign agent like a virus or bacteria, etc. But potentially, the same immune system can also turn against the host, and that can result in a disease called as autoimmune disease, and that can be lethal sometimes. So nature has provided mechanisms by which the immune system is kept in check so that it doesn't go around destroying normal healthy tissues. And for that, you have these PD-1, which is present in the T cells. And this is in a, let's presume a normal cell. So that has a ligand for that, that's PDL1. When these two bind, then the T cells do not become functional. The functionality is inhibited, and as a result of which, you do not have cell death happening. So this is the protective mechanism. As I said, the cancers are smart. So what they have done is they overexpress this, either the ligand or in the T cells you have the PD-1 which is there. So by overexpressing the PDL1, now the T cells are made impotent, as a result of which the tumors can survive. So here we now have monoclonal antibodies either against the PDL1 or against PD-1. So that interaction can be blocked. Once that blockage happens, the cells can be destroyed. The most important development, I would say, in the past decade is the development of these immune checkpoint inhibitors. Lung cancer, which was considered to be generally lethal, because by the time it is detected, it is usually advanced, either locally advanced or it has already spread. We usually treated them with chemotherapy, and most of these patients will have a longevity of 1 to 2 years. Now, in a percentage of individuals, maybe around 25 to 30% of the individuals with lung cancer, with advanced lung cancer, can be cured by these monoclonals. So that's a major development. And people have pushed the boundary of usage of this drug to what we call as an adjuvant setting. So if you pick up an early lung cancer, which is operable, you operate and then give the monoclonal so that the cure rates are increased much better. Why are we doing this? Because even though we have removed the bulk of the tumor in the lung, even though it is small, there is always a possibility that some of these would have seeded out as metastasis, which is not obvious at this point of time, but should come up in a year's time or 2 years' time. So by using these monoclonals, you are able to cure them much more than what otherwise surgery alone would have done. So you have a whole lot of these immune checkpoint inhibitors available in the market now. So they are predominantly useful in some of these cancers like the lung cancers, kidney cancer, a very aggressive skin cancer called as melanomas. Fortunately, melanomas are not that common in our country because we are all brown or dark-skinned. And essentially, melanomas usually happen in fair-skinned individuals who are especially exposed to high degree of sunlight with the UV light causing the damage. So you do have now people combining some of these immune checkpoint inhibitors to achieve a much better response as I see it. Now, what are the issues with these immune checkpoint inhibitors? Cost. The cost in US for a full course of immune checkpoint inhibitor therapy, any of these monoclonals which I listed out earlier, is going to be above 75 lakhs. 75 lakhs is not small money in our country. Not many, if you really want to look at it, I would say not more than 5 to 10% of the population would be able to afford it. So that brings a big problem here. And the second problem is not all individuals who are treated with this will be cured. There will be response, but the curability is around 25 to 30%. So which means you treat 100 people with 75 lakh therapy, 30 of them can be cured, so what happens to the remaining? So that's the problem which we are having now. People are working on identifying what we call as biomarkers to see within this 100, can you identify those 30 who are more likely to respond? That means you can use it only in them, and not in the remaining 70. So that is something which is actively going on. So hopefully we would have some additional information in the days to come. Other than this, you can also have toxicities. These are also potentially can cause side effects. One of the most important one is the immune-mediated toxicity or cytokine release syndrome, which can, in the early days when they started with this therapy, there were even deaths. But now we know how to deal with all that, so it's not a major problem. But neurotoxicity is also a problem with these therapies. So there are bound to be some side effects, so one needs to always balance and then take a call on that. And of course, the response is going to be there in what we normally call as cold tumors, which means there is a cold tumor is where the immunosuppressive microenvironment around the tumor is very heavy. So these things are not going to work in those individuals. Now I've just put down this table to just highlight one fact. You look at all the other points, the ones where I'm highlighted with yellow is the only area where actually this immune checkpoint inhibitors, pembrolizumab, has shown a true benefit. In my opinion, an individual should have at least close to a year of benefit, not 1 month, 2 months, 6 weeks, for some even say 4 weeks. That kind of benefit at a cost of 75 lakhs is not acceptable. You end up using up whatever resources that individual had for his family, and finally the family comes to the street because they have completely washed out. And this happens oftentimes. So you need to be really careful, and this needs to be discussed. And I'm sorry to say this, that unfortunately not always this is done, because oftentimes the oncologist will give you big promises and people go with that, but then the reality is something different. And after spending 20 or 30 lakhs, they are unable to spend more. There's nothing more they can do. They have already sold whatever properties or other things they've had, and they are completely lost. So if you look at the indications, there are only a selected few where you can really achieve something significant, in my opinion. FDA, however, authorizes the usage of these drugs if you have a progression-free survival of more than 4 to 6 weeks. What it means is, if the cancer doesn't increase by size by at least 50% over the next 4 to 6 weeks, it's considered to be a response, and therefore the drug can be prescribed. But it doesn't have to make an impact on survival. The survival, overall survival, is the key parameter. If the overall survival has very little difference with the drug or without the drug, it's meaningless. There are other ways of dealing with these patients' problems if it comes to it. The next one is the CAR T cell. This is a form of immunotherapy where we are developing a chimeric antigen-based T cell receptor. So, as I said earlier, T cells are the critical element for cell destruction, of tumor cell destruction. One of the problems is for the T cells to effectively destroy by identifying which cells need to be destroyed. So in the chimeric antigen, what we do is we take this part of an antibody, which is against a protein which is expressed in the tumor. For example, these are particularly useful in blood cancers and a condition called lymphomas. So they express what we call as CD19 or CD20. And these proteins, we have antibodies. So you take that and then you attach it to this sequence. The second generation has the co-stimulatory molecule and the signaling moiety. Using this new artificially generated T cell can now home in on the cancer cells, identify them specifically, and destroy them. One of the early recipients of this was a 8-year-old girl, I think it was 8 or 6-year-old girl, who achieved complete cure. And she is now, I think, 18 or 20 years of age. So you have excellent responses happening. Again, the problem is the responses are not in all individuals. Responses are likely to be in around 20 to, again, 30%, or maybe maximum you push it 40%. So this is one of the problems. And coming to the cost, so this is the different cancers which are now being treated with this CAR T cell therapy. Right now, solid tumors like breast cancer, lung cancer, etc., we do not have an effective one, although people are working very hard to develop a CAR T cell therapy for that, but it will take some time. The cost is simply prohibitive. $450,000 will amount to approximately 3.2 crores. Now, how many in a country would be able to afford that? Not even 1% of the individuals. Your insurance is unlikely to cover. West is getting bleeding, it's actually being bled because of the cost of these therapies in their healthcare system, because it takes away a huge percentage of the healthcare budget. The fortunate thing is, we are now trying to develop, in India, they have developed a vector, which is the costly component there, an indigenous vector in IIT Mumbai, in collaboration with Actrec, has developed this, and they have now started clinical trials using this Indianized version of the CAR T for blood cancers and the lymphomas. We are hoping that this would succeed, because then the cost is likely to come down to around 25 lakhs. Still, 25 lakhs is substantial, but compared to 3.5 crores, I would say is a huge, huge, huge development. Finally, I'm moving on to biotechnology. Biotechnology, I think most of you all are already aware that there's been a large facet where it can influence. It can influence agriculture, it can influence animal husbandry, fisheries, the human medicine. Almost all components can be affected, or you can have newer things developed with this. And that is one of the reasons why you find that in agriculture, using these resistant crops, you are able to save a huge amount on the fertilizer cost, etc. So thereby increasing the farmer's income. So these are all genetically modified farming products which are available. And coming to medicine, it's a huge area. A lot of developments have happened. I'm not going into the details of all that. Just to say that now people are moving more and more towards personalized medical care, meaning that for a given individual, you do not treat them with a standard. For example, if there is a cancer patient, you look at the cancer patient, study his tumor thoroughly, identify the mutations which it carries, and then target those important mutations. Drugs are available, at least in US it is available. In India it may take some more time, but some few drugs are available. Again, the problem is cost. It's still way up because these are all not yet generic, although some are generic. So that is one of the problems. And people are also trying to look at diagnosis, early diagnosis, and in that direction, again, biotechnology has helped. We have also developed a breast cancer early detection assay, which we are in the process of transferring to a company. So a lot of things can happen with biotechnology. It's a very, I would say, major field of improvement across the board. It's not just restricted to humans. It's across the board for plants, wild animals, animal husbandries, fisheries, etc. So everywhere you can have this impact, and that in turn brings about a huge development and benefit to the humans. So thank you for your attention, and I'll stop here and take the questions here. Thanks a lot.
Sir, how does the viral nature of viruses like COVID, which can adapt and change, react the viral nature of diseases like COVID?
Viral disease?
Viral nature, viral diseases in general, how does our immune system, adaptive immune system even react to that? If the COVID virus, if one immune system gains a sort of immunity to the COVID virus through the adaptive immune system, and the COVID virus itself changes and is infected again, is there any new reaction? And also one more thing, could you speak a little about cancer vaccines, how do they even work?
Okay. Okay, I'll first talk about the COVID question which you mentioned. Now, COVID, by and large, most of the individuals, if you really look at the number of people who had possibly been infected, not tested, possibly been infected, I would say close to 80% of our population would have been infected, but not tested. Now, they had been infected, but they were able to overcome that infection. It is only in a small percentage you find that the disease progressed because their immune system was deranged. Most of these people were elderly. They had some inherent immune problem, either in the form of diabetes or medications which suppress the immunity, by and large. When that happens, they were unable to destroy the viruses effectively, and that is one of the causes for extensive mortality happening as you see it. One important fact which we need to remember is that if you look at the number of deaths in our country, given the population size, the number of deaths, even though it was grossly underreported by the government, but it is still a fraction of what was seen in the Western countries. The reason is, if you look at the environment which we have, especially the slums, the Mumbai-Dharvi slums, we were worried, and I think everybody was worried, that that could be a major bomb waiting to go off, because you had the entire slum area where there was poor nutrition, poor hygiene, everything put together, and in that, fortunately, we did not find anything major happening. One of the facets here is our own immune system. When you are not so very anxious about washing your hands 30, 40 times in a day, but being a normal human being, what we were about 20, 30 years back, when we played, we washed, but then after that we ate anything, whatever was available. Nothing. That kind of situation possibly stimulates their immune system to a higher threshold, so that if there is anything to come up, it tends to become milder, because they are able to fight it out more effectively. One of the long-term problems which we are now seeing, at least in a small percentage of those who had been infected, is the long-term complications of COVID. And that is unfortunate, because people have debilitating lung lesions, and we have their capacity to work, capacity to walk also being compromised, because their lung reserve is grossly altered. Coming to cancer vaccines have been tried in the past. Basically what they are trying to do is, you take the cancer cells, heat the cells, or kill the cells in whatever way. One of the early ones, actually the cancer vaccines came a little later, but prior to that there was something called as Cooley's toxin. So this is a scientist, doctor, who took the bacterial preparation and heated them, lysed them, and then started injecting children so that you can have a response, immune response. And that actually seemed to have an effect on some of these tumors which they had. So cancer vaccines was a natural corollary to that. So what they said is, let's destroy the cancer cells by whatever means, and then inject it back to the patient into the dermis or subdermis. Allow the immune cells now to see these dead cells. So it's a form of immunogenic death, so that it can trigger a better response. And that seemed to work in a small percentage. It's not a routine usage, but in a small percentage, it did seem to have an effect.
You mentioned many different types of treatment that you can go in for a cancer patient. And there are also many types of cancers. So how does a doctor decide which form,
Therapy to choose.
which pathway to take and...
Okay, so see, each tumor arising from a particular given site behaves differently. Let's say, for example, let's take the breast cancer itself. Breast cancer is not one entity. You have different subtypes within that which have been identified. As it stands now, we have 4 different subtypes. But within these subtypes, you are likely to have additional sub-subtypes also. So the treatment for these subtypes are different. The general consensus is that you need to take the treatment has to be based on the stage of the tumor, whether it is localized or whether it is spread to the lymph nodes or whether it is spread out. Number 2, whether it is an aggressive tumor or not too aggressive tumor. Number 3, whether it is expressing some proteins which can be targeted. Like, for example, the estrogen receptor and progesterone receptor on one hand, these are all good things, good factors because they have good drugs for that. Or HER2 protein, which I mentioned, which has an antibody against it. But it makes the tumor very aggressive, but this antibody helps in completely destroying that. So you need to study the tumor in complete. It's not as if you walk into a hospital, they do a biopsy, and immediately you're given your treatment, this is how it is to be done. No, you need to study that more carefully. More and more now people are moving into this personalized medicine category because you study these tumors, you also look at tumor mutations which are there, whether you can target them as well. Maybe initially you may not, but at some point you can always consider using some of these newer drugs. But the general consensus is, if it is an early breast cancer, you can have to operate initially. Now surgery, if it's a very small tumor, you don't need to lose the breast. You can just do what is called as breast conservation and irradiate the rest of the breast so that recurrence doesn't happen on that side. Then treat them with additional chemotherapy. So that's the standard. If the receptors are positive, you can treat them with drugs like tamoxifen, which can target this estrogen receptor basically. On the other hand, if it is an advanced cancer, locally advanced cancer, spread to the nodes, you treat them with chemotherapy initially, shrink the tumor, give radiation, shrink the tumor, and then do the surgery. Or alternatively, you can do the chemo first, shrink the tumor, surgery, and then radiation. So there are different ways of sequencing these therapies. So the decision on what you need to do will depend upon the patient, the size of the tumors, etc. Age is also an important factor. Very elderly people usually have high levels of this estrogen receptors. And in some cases, we don't even operate. We put them on this anti-estrogen drugs, which shrinks the tumor completely. If needed, we can always operate.
Check. Thank you for that wonderful talk. I have a question, which is, you did point to costs of these various therapies. And of course, these are developed by Western countries. So what do you feel should be the way some of these things need to be reported? Because clearly there's a lot of public investment that will have to go into the development of some of these therapies. And are most of the costs associated with the ecosystem that is there? Is it something that can be done a lot cheaper? I mean, you did point to one of them being, can be done much cheaper. So what are the various sort of ways in which, if reported right, would then lead to more investments and cheaper therapies?
Okay, I would take the example of Cipla. When the world over HIV was rampant, the Cipla founder, he said he can offer the triple drug therapy for $1 a day cost. Everyone was taken aback. Once they heard this, other major institutions, they came about and said, we will support this. So by having the large scale, they were able to do it. He was able to do it. Now, we need these monoclonals, for example. Now, you cannot wait for 20 years for the patent to come off and then you have the generic. So I can tell you that right now we have a program which is funded by the Department of Science and Technology, where Cancer Institute is partnering with IIT Madras in developing some of these monoclonals for therapy. We are also developing monoclonals for diagnosis. The institute had identified early markers for early diagnosis of ovarian cancer. Ovarian cancer is a killer disease because you do not have symptoms. And most often, by the time a lady comes to the hospital, it is very advanced. And the cure rates or control rates is only going to be 25% or less. So early diagnosis is the criteria, this is a very important one, and we are working with them towards that as well. So I think the focus has to be, can you do it in the country? Yes, you can do that. It is not difficult, it requires collaboration, and if you require sustained funding. I would say sustained funding because by and large, if you look at the funding agency, they give you funds for 3 years, maybe max of 5 years. At the end of that, you have to go back, which actually, I would say, becomes stressful because you don't know whether you're going to get your next funding or not, in spite of whatever you have shown. We were fortunate that we did have a funding which went on for more than a decade, and that allowed us to develop markers for early diagnosis for cervical cancer. We developed an assay, we have transferred it to Hindustan Latex Limited in Trivandrum so that they can develop a kit which can then be validated. We also have this breast cancer work directly coming out of that and few other targeted therapies as well. So I would say that if there is a sustained funding which removes this cycle of going back and forth, that would definitely help in achieving what one wants to achieve.
Sir, I have a question which might be very naive. So you talked about all the diagnosis and cure, the modalities and developments in the cure of cancer. So do you have any guidelines as to what are the good practices that might even prevent the
cancers?
Yeah, if are there any such things which a doctor can say about that?
No, you do have. See, the thrust now is cancer prevention. If you want the facts, close to 55 to 60% of the cancers which we see in our country are preventable. Number one, tobacco in any form causes almost 40 to 45% of the cancers in our country. Second, alcohol causes around another 5 to 10%. Third, virus-induced cancers like cervical cancer, which is associated with human papilloma virus, for which we now have a vaccine, the human papilloma virus vaccine, HPV vaccine, as well as also hepatitis, liver cancer. You have vaccines against hepatitis B and hepatitis C. These actually can reduce that 50 to 55 of 60%, 60 numbers out of 100, these can be reduced. So along with this, by simply having a better healthy lifestyle, having plenty of fruits, vegetables, which increases your antioxidant levels, avoiding red meat, I'm not saying don't take it in moderation, have plenty of fish is the best, next is chicken, your red meats come after that, and fruits and vegetables in plenty. Exercise at least for 45 minutes. These, I think, will ensure that you don't put on weight because obesity itself is a factor for several cancers. So, cancer per se is preventable. There is likely to be 30 to 40% where whatever you do, there may be a possibility, but then the question is, can you pick them up early? So in that context, a lot of work is happening.
My question would be, how early should women get done with their screening for breast cancer? Like, what's the ideal age, and what are the tests and screening available in India right now?
Okay, thank you. That's a good question. If you're talking about breast screening, we would say that from the age of 25, the ladies practice self-breast examination. That can go on. You need to be taught by a good clinician, a gynecologist or an oncologist can help do that for you, train you in that. And from 40 years onwards, you can then go on to do the yearly mammogram. Usually, younger age group, mammogram is not that good because breasts are too dense. But if there is some suspicion, people can use MRI along with ultrasound. So these are some of the tests which can help. Mammogram can then be continued till the age of 65 or 70 years of age. So that is the general dictum. There's one caveat here. There is an entity called as hereditary cancers. That means you have a faulty gene being passed on generation after generation. So from mother or grandmother to mother to the daughter. These hereditary cancers occur much earlier. When I say earlier, by and large, most of the breast cancers, if you look at it, they usually occur beyond 50 years or 55 years of age. The cancer which occurs under 35 years of age, in our definition, in the West they say 45, but we see a large number of 35 years of age, so we use that as a cutoff for gene testing. So we can use gene testing to identify the BRCA1 or BRCA2 mutation, and if you do find that in a patient, then you can allow screening for that same mutation in the other members, and then institute measures so as to prevent cancer from occurring, to pick it up early. So in those instances, you will start not only self-breast examination, you would also do MRI with ultrasound till the age of 30, from 25 to 30, and 30 onwards, beyond 30, you alternate mammogram with MRI. So this is for the very high-risk group, that is where we have the mutation-positive people. But that's not possibly likely to be there in 5 to 10% of the women as such. Another important caveat here is that, unfortunately, the incidence of breast cancer is increasing in our country grossly. 10 years back, cervix was number 1. Breast has overtaken that. The reason for that is multifactorial. Number 1, your lifestyle changes. You have the eating habits have changed. If you look at the traditional Indian diet, it's well balanced, everything is there, everything is fine. But when you start having these fast foods, you tend to have the potential to capture more of calories. As a result, obesity itself triggers off a whole lot of problems, including cancer. That is number 1. Number 2, 30 years ago, our house never had gadgets. Your grandmothers and mothers had to do whatever the work by themselves. Of course, some had the maids to help them, but by and large, it was them. So whatever calories they took was spent. It's not the case now. Unless you do exercise, you're not going to spend that. The third, I would say, important factor is the first childbirth after 30 years of age. This is important because the risk for breast cancer increases. I'm not trying to say you shouldn't, or you should have your child before that, or people shouldn't focus on their careers. I mean, this has changed. 30 years ago, the girl would have been married at the age of 18 years, and by the age of 25, she would have completed her family. Right now, that's not the case. You have the studies, then post-graduation, then getting into work. So by the time you settle in, you would be beyond 30, and you would like to wait till you are stable enough. Everything is fine, but please remember that a first childbirth after 30 years of age is a strong risk factor for breast cancer. And that's primarily because there is an unopposed estrogen acting on the breast. Estrogen is proliferative. So therefore, that is something which one needs to bear in mind. So with healthy lifestyle, you should be able to take care of yourself.
I just wanted to shift the topic away from cancer and follow up on the first question that was asked. I've never quite been able to understand what drives variations of the COVID virus, for example. Why should a virus develop variations? Is it an evolutionary survival mechanism? Is it accidental? And I've not quite followed that.
No, it is evolutionary.
Okay.
It is evolutionary because if you let's take the COVID itself.
Yes.
It's an RNA virus, right? And RNA viruses have this potential for mutations happening manifold compared to the DNA viruses. And it's a matter of natural selection. It tries a different permutation, it needs to survive, because the immune system has seen it. So the next time it is going to come, it will be thrown out or destroyed. So it has to have a way to protect itself. So in that situation, it tries to mutate some of these moieties and thereby tries to avoid being detected by the immune cells. But you have vaccines and natural immunity, especially I think the vaccines which were used with using the whole virus, in my opinion, the whole virus is far better than the spike protein based one, because you are having a repertoire of antigens available for the immune system to see, and therefore, even if there is mutation in one protein, you have others to fall back on for the immune system. So that is something which is natural, and this is the evolutionary pressure. The same happens in tumors. In a tumor, when you take the biopsy initially, and then you study that, and then treat them with chemotherapy, radiation, whatever you want. You are exposing the cancer cells to lethal drugs. So the cancer cell fights back by developing mechanism to prevent death. And some of these are targeted to acquiring mutation which will allow them to survive better in a hostile environment. So this is a process of natural selection, which is unfortunate because that's the one which will finally kill, because the more mutated they are, they escape the conventional therapies and possibly spread, and then death happens.
But I'm sort of puzzled by how the virus knows it wants to survive. It's not a conscious thing, right? So this is something about natural selection that I don't understand. I mean, I was curious.
It is natural selection. It is basically a natural selection because you're putting a pressure on the growth of those viruses. So over a period of time, if there are 1 million viruses in a given individual at a given time, 990,000 would get cleared out. Maybe 100 to 10,000 may survive. And these, if you study them, you'll find that they have undergone changes. This happens also with bacteria. You treat them with antibiotics, you misuse the antibiotics, they acquire resistance. So when they come back next time, they are not affected by the same antibiotics anymore.
Thank you.
Thank you, Professor Rajkumar. I think that was very informative, and I hope it spurs students to read more about biology and ask the questions of professionals in this area. So our next speaker is Nandan Sudarsanam. He's a faculty member in the Department of Management Studies and a core member of the Robert Bosch Center for Data Science and Artificial Intelligence, and the co-head of the American Express Lab for Data Analytics, Risk and Technology at IIT Madras. He earned his PhD from the Engineering Systems Division at MIT, following which he has worked as a quantitative researcher for 5 years at a high-frequency algorithmic trading firm in New York. His research and work experience focuses on applications of experimentation and machine learning. This spans data and problems across different domains, including but not limited to finance, urban mobility, digital platforms, civic services, sports, and criminology. He serves as an associate editor of the Informs Journal of Data Sciences, and he publishes in machine learning conferences as well as peer-reviewed journals in engineering and applied statistics. Please welcome Nandan Sudarsanam, and look forward to an interesting talk on machine learning and artificial intelligence. Thank you.
Thank you. Thanks a lot for having me over. Thanks a lot, Sashi, for inviting me, and thank you for the opportunity to talk a little bit about AI and ML. So this is what I do research in. This is what I teach at IIT Madras, and something I'm passionate about. And passionate even before it became a very hot area, by the way. So need some credit for that. So I thought I'd start a little bit. So I've got a very brief presentation about 20 minutes or so with some examples, and I thought I'd give some time for Q&A. And we can make this an interactive session. So feel free to raise your hands even if during the presentation you have a question or something. Okay? So I thought I'd start a little bit about what is AI and what is ML. These have become kind of buzzwords. And unfortunately, when things become buzzwords, people kind of use them and misuse them quite a bit. AI has a very different meaning in academia and from a theoretical sense, and when it was coined versus how people are actually using it right now. So I thought I'd be a little bit of a purist and tell you what really it was supposed to mean when it first came out. So if you look at AI, it's a kind of umbrella term, right? Which kind of talks about the notion of making machines behave intelligently. And as you can tell, the word intelligently is a very subjective word, right? It's what you find intelligent is different from what I find intelligent. It's not saying it's going to make machines behave rationally. It's not saying it's going to make machines behave superior, faster or something that I can clock. But intelligently is my perception, and so it's a human perception of what behaving intelligently means. And the other key part is it says behaving intelligently. It's not making machines intelligent. No one is as stupid to kind of think that the machines are becoming intelligent. This is not a Terminator 3 scare show. So we're very clear about it. When we say we are talking about making machines behave in a fashion that we think is intelligent. What is intelligent behavior? You could think of it as, well, if you can get the computer to play chess and beat someone, that's intelligent. If you can get the computer to maybe write an article, it's kind of intelligent. You need to understand something. You got to, again, behaving intelligent. It doesn't understand the article it's writing. It's doing something. So that's AI, in a sense. And I'll try to go through a little bit of a brief history of AI also in the next slide. But now, what is machine learning then, if this is AI? Well, machine learning is a subset of this space and an application of the artificial intelligence. So it's a little bit more applied. And think of all the ways in which you can behave intelligently. One way, just one way of behaving intelligently is to learn from data. Right? I can do a lot of monkey see, monkey do. I can tell you to behave in a certain way. I can say, every time you see this particular move in chess, you go do that move. To the computer, I can tell it to do that, and you might perceive that as intelligent behavior, and it would fit the bill of artificial intelligence. But in machine learning, you're saying, no, 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 no. You behave intelligently in many ways, but one way of doing it is to learn from data. So there's a layer of intelligence, a specific layer, that pertains to learning from past instances and doing something. There are many ways to behave intelligently. One way is to learn from data and thereby accomplish the task of behaving intelligently. So that's why machine learning is a subset, and it's a more applied area that focuses a lot on algorithms that help you to learn from data. We'll go a little bit more deeper into this, and in fact, the rest of the talk, I'll speak a little bit more about machine learning specifically rather than AI in general. You might have come across other terms like statistical learning, data mining, pattern recognition, and so on. Many of these are different flavors. Part of the reason they have different names is they came from different fields. So if you think about statistical learning, right, even before the first computer was ever built, this business of learning from data is something statisticians have been doing. Right? So it's nothing new to them. So a kind of field that tries to unify the knowledge base there and build off of that into what modern-day computers are doing is statistical learning. Similarly, with the IT boom, there was a lot of data. So looking at it from an IT perspective in terms of databases and data sets, and then saying, I have this database and this data set, how do I from there go to the task of learning, is more focused on data mining. And pattern recognition, again, another flavor of the same thing, right? One way of learning from data is to recognize patterns in the data. Right? So many people in signal processing, which is speech, vision, computer vision, and so on, are in the field of pattern recognition. But I should honestly mention that there are huge intersections between these definitions. Obviously, you can see that. And it's more that many of them come from different fields. Right? So maybe next time you recognize some of these words, they won't seem so different or scary. Okay, so what happened with AI, right? So AI has a very interesting story. Back in the late 60s, a whole bunch of scientists who were talking kind of theoretically got together and said, man, this is it. This is going to become big. This is the future. The notion of intelligence being moving to the machine at some level seemed very real, seemed very possible. And so a lot of the smartest minds wrote a lot about it. And at that stage, it was still very science fiction-y, right? So what happened was a lot of funding went into it. And what happens when you take something too quick, too early, is what happened. What we then saw was what was called the AI winter. People made a lot of fun of you if you worked in AI. The machines were not that great. So none of the things that seemed to be promised, all this vision, ever really happened. People were not doing any of that. Nothing happened. So it kind of went through a huge slump, actually. So it's hard to imagine that, right? Right now, AI is such a big buzzword. To think that it actually boomed at one point and completely crashed, it was such an insult if you kind of said, it was like irrelevant. You're working on something irrelevant. You're working on something hyped up. You're wasting public money, kind of a thing. No one would dare say that to someone working in this field now, would they? Right? Now, what has since happened is it slowly starts percolating in industry. People start seeing value. But it's back now, and it's back in a big way. Nobody's making fun of it. But what really happened? So I think 3 things happened that allowed for AI to become big now, and that totally killed it back then. The 3 things are, if you want machines to behave intelligently, you need machines. Okay? The machines were not great back then. They were not fast. They could not store much. Sure, in principle it can, but you really need the evolved human being to be intelligent, right? You can't just take it and put it in a box and expect it to work well. The second thing that has happened is the algorithms have gotten much better. Some of the ways of looking at it, and again, partly owing to computational speed and so on. So we've also seen a marked improvement in the way logic is being applied in these machines. So it's an improvement in algorithms in some sense. So it's the data set size, the ability to have the machines, it's the processing. But I personally think the third thing is the most important, which is we've moved a lot of things onto the digital platform. And this thing works really well then, right? Like imagine what's the scope for AI if 10 people are meeting and having a conversation? 10 people are meeting and having a conversation, and you find that relationship meaningful, and it ends there. Now, suddenly, I've moved that onto a digital platform, like Facebook or something else. Now, suddenly, there is scope for playing with the system, right? Now, suddenly, there's scope for who should I connect with whom. So similarly, we've seen commerce move from the physical commerce, grocery stores, all the way to the digital platform there. We've seen finance move onto a digital platform. We've seen networking move onto a digital platform. The existence of life on digital platforms makes this, we're now poised for AI and ML to do things on this platform. So it's become, again, relevant. And that is the reason why I believe that this is here to stay, in some sense. You could always make an argument for whether it's overvalued or something. I mean, some people always said, IT was overvalued, and there was a boom. But IT has not disappeared when the boom crashed, right? And that's probably the same thing we're going to see now, which is, even if it's overvalued or overhyped, sure, but it can't go away, right, in some sense. Okay, so I wanted to talk a little bit about machine learning specifically, but I thought more than just giving you this slightly wordy definition, and specifically one area of machine learning called supervised learning, I'd do it through examples, right? So I wanted to talk about a couple of examples. Many of these are very popular examples, so some of you might have already heard them, so bear with me. So let's talk about the first one, spam, right? So these are just examples to help you understand what supervised learning is. So one of the most common examples given is, so you receive email, and you sometimes want to classify it as spam or not spam. So what's a smart way of doing that? Well, one way is to have someone kind of figure out what constitutes spam email. So someone might say, if it says free money from Nigerian prince, spam, right? If it says something else, spam, right? Like, so you can write a set of rules. But remember what machine learning said? The use of algorithms that can learn from and make predictions on data as opposed to traditional programming with instructions, kind of the definition I used previously. This idea of doing it through a set of rules is always going to be problematic. One, because who wrote the rule? how do I decide, should it be free money or should it be free money from Nigerian prince? Okay, who comes up with these rules? I mean, how do you decide what is spam and what is not? That's one problem. And two, once I fix the rules, how often am I going to go update it? Second, what if my spammer or hacker just decides to change? These are all problems with traditional programming with instructions. So I'm going to take a slightly different approach. With machine learning, or supervised learning specifically, I'm going to create a target, and the target variable is spam or not spam. So it's a variable called is it spam, and the answer is yes or no. Okay? And I'm going to collect a lot of data. Data of spam emails and data of not spam emails. And I'm going to try and define an email in a slightly mathematical way. So how could I define the email? I could say it contains the word X, it contains the word Y. So there's still some scope for the humans to come and tell us, saying what are things that typically constitute spam. And so this is what we call feature engineering, trying to figure out the right features associated with an email. Another feature could be the length of the email, right? Number of words. Another feature could be if there are special characters in the emails. Another could be the subject line. Another could be whether the sender is in your address book. So an email is stripped into a whole bunch of features. These are what we call the inputs. And we get many instances of many emails. And the output, or the target variable, and this is, I'm trying to link it to the definition I have out here, is whether an email is spam or not, the 1 or 0 associated with it. Now with this data in place, is there a way for me to run algorithms that learn from this data such that if these features are present, it tends to be a 1 in the 1 versus 0 on the spam spectrum? Whereas if these values are seen, it tends to be a 0. So in a sense, I have not written a single rule. I have only provided a machine with the information about the email. I've extracted it as a set of features. Email 1, 200 words, sender from the address book, does not have the word X, has the word Y. I create a lot of features. So every email is stripped out like that. And finally, I only tell the machine saying, was it spam or not? And then the only thing I do is I write a piece of code or algorithm that says, now go learn from this data. Tomorrow, I won't tell you if it's spam or not, but you should look at these feature values and tell me whether you're likely to call it spam or not spam. So it learned from the data. So now what I need to do is, again, I didn't write a single rule, right? So even if my intuition was wrong, the algorithm is not going to get fooled in some sense. And all I need to do is change the data as time goes by, and it learns new things. So if it's a moving target and someone is changing the way they do spam, you just need more data, and you'll get it right the next time around. So here's another example. Another one might be, what should be the price of a house? So the first example, the target variable was spam or not spam, which was binary. The second example, I'm trying to predict the price of a house, and the output variable is therefore a rupee amount or a dollar amount. That's the target. Again, what am I going to do? I could say, come up with a set of rules. A real estate guy will say, if it's in this neighborhood, if it's this much square footage, if it's this much, I'm going to give it this price. Again, I'm going at it in a rule-based way of thinking. I don't want to do a rule-based way of thinking. So what do? I gather data. I gather data about houses. And I strip a house into a set of features, such as distance from city center, belongs to neighborhood X, square footage of the house, number of bedrooms, So I take a house, list it as a set of features, it's a vector, and I get many, many, many instances of houses, and then I get their corresponding prices, right? And then I feed it to a machine which learns what the relationship between the inputs to the output is, such that tomorrow, all I need is the set of the features, and I'll get a prediction for what the house price should be, right? And you can think of many uses for this. I was also thinking, saying there might be many other examples that are relevant to journalism in general. For instance, what do you think, how do you think you should classify articles by topics, right? One way to do it is to have somebody sit and say, this belongs to X, this belongs to Y, but that might not be sustainable for Google. Google actually goes and Google News goes and scrapes millions and billions of articles on the internet. How do you automatically go put them into buckets, right? Again, you create an algorithm which has a lot of data, which takes every article, strips it into a vector, right? And then you have a set of outputs where people have said, this article is sports, this is business, this is something else. And an algorithm learns, right, that this is the typical relationship such that even if you don't provide the labels tomorrow, by just looking at the article, you can automatically place them in bins, right? Now, of course, a lot of advances have happened where one area that's of a lot of interest is in natural language processing. So not only are we doing simple things like saying, does the word exist or not, more understanding of language through semantics is an area that's actually come up in a big way. And another thing that's also been very exciting is generative models. So generative models are ones where you're not just making a decision or making a prediction. Those are called discriminative models. They discriminate between spam and not spam, right? They try to make a prediction of Y given some X. Generative models create Y. So if I've become good at telling you what is not spam and what is spam, can I create a spam email? Can I create a not spam email? Can I go the other direction, basically, right? For a given house price, can you describe a house for me? Can I write some? So if most of what machine learning has been, up until recently, has been to say, given something, I'm going to tell you if it's a yes or a no, or make a prediction on the output given the input. But generative models co-create the input and output because I've understood the relationship between the input and output. And a very popular thing now, like ChatGPT or Bard from Google, is exactly that, which is creating content rather than discriminating the content. Okay? Another area that's also popular is unsupervised. So for instance, let's take a look at this Google classification, right? How do you think Google would go about creating a model? So let's go back to even the Gmail example, the spam example. So it's very easy to think about how an email can be stripped into parts. It's very easy to count the number of words in an email. But how do you get the labels called spam and not spam in the first place? Your goal is to, given an email, figure out if it's spam or not. But the first thing you need to do is get instances of spam and instances of not spam. Instances of emails are easy, right? And counting the number of words in the email is easy. And seeing if the word X is in the email is easy. But how do you know if it is spam or not spam to begin with? Some warm body at some point had to tag it as that, right? And that's the problem. It's easy for Google to get 1 billion emails and quickly create that X matrix, but it's very hard to get output labels. So the whole field of unsupervised learning is when there is no output label, can I still do something useful with the data? There is no signal guiding us in the end. There's no target variable like supervised learning, but I still want to do some kind of pattern recognition within the X matrix. Okay? I'll jump to my last slide here and open things up for questions. Another very exciting field that has come up is called reinforcement learning. So what is reinforcement learning? Well, a lot of times, especially in supervised learning or unsupervised learning, the output is a prediction. The output is a pattern that is recognized somewhere. Okay, so how does that help? Well, if you predict something, then maybe I can make a business decision based off of that. I can make a decision, right, to do something with it. Reinforcement learning says, well, my end objective is to do something, not to predict something, not to learn something. But when you have to do things, so reinforcement learning is the area of machine learning that has to do with controlling actions, responses, and operations. So it's a doer, not a learner. But to do something effectively, you have to learn about it, right? So the learning is happening, but it's implicit. It's under the hood. The key thing about reinforcement learning is that autonomous driving, for instance, it's no point that machine learning comes and tells you whether you're going to crash or not. You slow down the car, for me. So take chess, for instance. There's no point in making a prediction that if you move the pawn, it will get sacrificed. Well, then don't move the pawn or do something else. So unless you do things, you don't know what's going to happen. So therein lies a more complex problem of not just looking at the situation at hand and making a prediction, but the whole notion of learning from doing. Like if you think about how you learn to cycle, it wasn't through supervised learning or unsupervised learning. Supervised learning would mean you took a lot of data of possible things to do on the cycle and whether the outcome was crash or not, and you learned it at one shot. That's not how you learn to cycle. You didn't look at multiple examples of people cycling and learn to cycle, right? At the same time, you did what did you do? You cycled. You tried something, it worked, it didn't work, you crashed once. So there's a very interactive way of getting data where you do, get data, and do it better. And when you learned that crashing hurt, you stopped doing it. You didn't, for the sake of learning, just keep crashing again and again to do things. So the natural mechanism by which you start doing sensible things, but you're always gathering the data. Your output is still, am I cycling well or am I crashing? And so there is learning happening under the hood, in some sense. There is some supervised learning happening, but the end goal is to learn to cycle, not to predict whether you will crash or not. So reinforcement learning is something that's taken up in a very big way, ranging from autonomous driving to beating the best chess players to operating cooling plants and things like that, where operation and doing is key rather than just learning or predicting. So I'll stop with that, and I'm happy to take questions from everyone. Just grab some.
Sir, does AI need humans? Because we've been talking about how AI is taking up jobs in IT sectors and how AI will take over manpower. So does AI really need humans or it doesn't?
So does AI
need humans?
Yeah, so we're very much at the stage where humans play a very critical role in effective AI, even for AI to do its job. So there are two different parts out here, whether AI will take our jobs and replace us. So how much will it hurt us? And then there's the other question, which is, for AI to be effective, does it need humans, or can it just do it with data? Well, I'm of the firm belief that people are moving towards AI being less reliant on the human intervention, right? So one of the big things that we've seen with the neural networks and so on is that it gets away even without a lot of feature engineering. So for instance, you need to even tell the AI what features to look for in an email, right? You don't have to give it the rules, but you at least have to say, in an email, look for these words. They might have a relationship to your output. Even if you don't say that it has a relationship, because if you did, that would be a rule. You at least had to do a lot of feature engineering, is what we used to call it. But now, a lot of algorithms are robust to even that. So you can just throw all kinds of data at it, and it'll figure out what the relationships are. But a big part of AI working is called human-in-the-loop AI, right? Many times AI learns by looking at how an expert behaves. Many times AI learns from querying an expert. What would you have done in this situation? And that becomes data that it learns from, right? So there are lots of paradigms of AI learning from humans and needing humans for it to do a good job. Otherwise, it's just garbage in, garbage out to some extent. But there is also a lot of research on, can I be even less reliant on the human? If the human lied to me, for instance, how robust can I be? If there's a systemic bias in humans, how can I overcome that? And it treads on things like fairness. The biggest examples given are loans and biases in the way loans are given to across genders or race. So is there a way for AI to kind of overcome that? So compensate for human this thing. Can AI be made more safe, right? Can AI be made such that if the human was chronically missing something, it makes up for it? And can we then also learn from the smartest experts, right? Something that we would have never thought of doing, where we specifically query certain parts where the AI is weakest. So one very active area is called active learning, where AI realizes that it's terrible in certain kinds of, so should you operate or not? Or is it spam or not? Well, sometimes the AI gets it perfectly correct, and sometimes the AI gets it kind of wrong. Can I escalate just those issues to a human so that I get more data in that region and I can become better? So lots of smart paradigms which work with humans, either to correct for their biases or to tap into their genius. Now, the second part is an often talked about thing of AI taking away jobs, right? I think it's a part of a broader thing, which is any automation at any point in time has taken away jobs. It has taken away and provided jobs. So it is not the raw numbers that ever worry me, because you will always have newer, more higher paying jobs. But its effect on inequality is bound to be there, because historically we've also seen that any form of automation has created more jobs than it's taken away in some sense. But it has also left us at a place where the inequality has widened, right? And people who were at lower paying jobs are going to face the brunt more than people who are at higher paying jobs. So I don't see why it would be any different with this in some sense.
So a little bit earlier you talked about chess. So there are chess bots like Stockfish and AlphaZero, and also ChatGPT can also play chess. I mean, very badly, but it can still play chess. So what's the difference between these three things?
Yeah, so I'm not too familiar with ChatGPT's chess performance, but I'll talk a little bit about Stockfish and AlphaZero. One of the most fascinating things about Stockfish, is the algorithms kept on getting better and better, right? With being able to do deep learning. Deep learning is nothing but something called artificial neural networks with many, many, many layers, for those who know how an artificial neural network looks. And a paradigm shift with deep learning was that before it was seen as almost untrainable, but now it's trainable. But in the end of the day, right, Stockfish essentially is a supervised learner. The example that I gave you, where a whole host of chess games, and I believe Stockfish uses, I think, 80,000 or something like that, critical chess games, and actually learn saying, if you do this, the likelihood of this happening is so much. It's like a corpus of data that is ingested, and relationships are being learned. What makes AlphaZero really great is that it uses the paradigm called reinforcement learning in a big way. The joke is that AlphaZero learned to play chess. It wasn't fed chess games. It wasn't fed a single chess game. And it learned to play chess in 4 hours, essentially by playing against other chess computers and playing by itself. Because remember, reinforcement learning is the paradigm of doing, not just predicting. So it did it. It went and it played a game, got a response, played another move, got a response. So it just keeps playing against itself, and it keeps playing against other chess computers. And so it's learning in a way that you learn to cycle, versus Stockfish, which gets a corpus of games and learns what is generally good and bad. And that's why AlphaZero has been so exciting and probably the strongest chess computer right now.
So what about ChatGPT?
ChatGPT, I don't know its chess playing ability, because ChatGPT's intent was never as much chess. Its intent was generative models, right? It's creating access. So you can still think of this as the target as y. In a game like chess, the output is y, where y is winning the game. You can have temporary small y's, which are, I want my board position to be better midway through the game. You can say after X moves, the opponent should have lost more pieces than me. So you can create other minor output variables, but you do have a terminal output variable, which is checkmate in some sense. It's 3 classes, which is you win, draw, and you lose. So it's a 3-class output y. But you can have many intermediate why. So in a sense, a discriminative model should take care of it. You don't need to create new games. You need to win existing games.
So there's a theory of sorts that AI will eventually take over human minds and human existence, and we're all currently talking about ChatGPT and Bards and Ernies, but how does that influence the human ability to think, and will AI eventually replace what we can term as the human influence in every sector?
Yeah, so I do think in places where automation is happening, people will lose jobs, and things that are kind of mundane will understandably go away. And not just mundane, things that are easily doable, right? And I do think AI is almost at the point where it can start fooling people quite a bit. For instance, if you read a ChatGPT output and a human's output, it's hard to tell. We will still be good enough to, the smarter ones can write pieces of code that will figure out the difference or try to fool ChatGPT, and you can fool it quite well. But this whole notion of this evil AI, which is going a step further, because things like consciousness and so on are still very hard to understand, and it's still, for me at least, perhaps I'm limited, I still find it hard to imagine a conscious AI, right? So there's a lot of fear-mongering on that front, which is that there is an evil, there's a sentient being that will this thing, and again, maybe I'm just limited, but I find that very hard to imagine, because nothing that we work on is that, right? But then there are people who argue saying consciousness is itself an emergent property. It's not an inbuilt property, right? It emerges. But I kind of buy what Andrew Enge said on this topic. He said, worrying about that when we're so far away, particularly against this conscious and sentient AI, is like trying to prevent overpopulation in Mars without getting there, right? I cannot be, perhaps it's a problem, but I can't be productive about the problem without going there. And we're so far from that notion of sentient and conscious and evil AI, that it seems meaningless to kind of worry about that right now.
So I wish to ask a question regarding ethical dilemmas a machine can take in, because when we talk about autonomous driving, it will encounter a situation where it has to abide by the law, but then it can even kill people. So starting with that, we are actually transgressing into the areas of humanities where interpretation, as you beautifully pointed out, intelligence is very subjective. So how will it perpetually be with us as a subservient, subservient to the human beings? So your take on these things?
Perhaps I have a slightly biased view on this. And I'm willing to own up to the bias, which is I think any of these things should be measured by how much safer they are. If I can show you that on average I'm safer through some X standard deviation safer, that I might not get it right every time, but I'm just safer than a human. Sure, I give out loans, and perhaps my algorithm might have some bias, but I'm less biased than, and I can prove it to you in terms of bottom line, than a loan lender who, has historically never given loans to a particular race, or the number of human errors that happen in certain places are just raw numbers much higher. Then that's when I say, you give me a free pass because I'm on average safer from a utilitarian perspective. But of course, not everything is a utilitarian perspective, right? A big part of this is not that humans are safer while driving as well, and autonomous driving is no exception to it. It's the notion of culpability, right? It's a notion that you took that decision, you are to blame, I can point my finger at you. When the AI takes a decision, there's a deep discomfort saying, I can't point my finger at something, even if I can show you through first principles and logic as to why that's the best decision, and even if I can show you through utilitarian terms that on average I'm much better. It makes people deeply uncomfortable when you can't point a finger at something. But I do think, therefore, it's high time to do something that we have not been able to do, right? Which is come up with moral and ethical frames of reference. I think you're all familiar with the trolley problem, right? The train is going on a track. You let it go in the same direction, it's going to kill 10 people. But you can pull the lever, and the train will be diverted. But when it's diverted, it kills 2 people. What's the right thing to do? A utilitarian will say, I should pull the trolley, pull this thing. But it's very easy to come up with examples where you can't just take a utilitarian perspective. Again, there the onus was on the fact that a human was making a decision. If the human did nothing, there's no blood on his or her hands. But how will you answer the question, the parents of the 2 people that you killed? You chose to do it, right? Who gave you the authority to do it? So there's a lot of these questions, and again, these are philosophical questions, right? These are not necessarily, but those dilemmas have existed with us, and it's not dilemmas that are coming up because of AI. It's just that we were comfortable not answering some of these in the past or having, firm conclusions about them. And I say this is as good an opportunity because again and again, we are seeing that from a utilitarian perspective, it is safer and better. And from a first principles perspective, it is following clearer rules. So why not?
Sir, I read this article about the ethics of AI in the Mint today by Jaspreet Bindra. So he made 2 arguments. One was the environmental impact of AI, and one was the moral and ethical impact. So in the environment, I didn't quite understand it entirely, but under the environmental impact, he said that training a transformer model just once requires 213 million parameters. And this is the CO2 emissions which are produced by this is equal to 125 flights from US to China round trip. And ChatGPT 3 requires actually 175 billion parameters. And under the ethical argument, he said that the model of AI is amoral, and it doesn't know what it's doing exactly. So it's just taking information from the internet. And so all these AIs, when they take information from Reddit, Wikipedia, from the net, most of these are basically 85% of their users are men, 67% of Reddit users are men. And the open source images that AI uses also, they also have a Western male bias. So sir, how would you sort of counter these 2 arguments?
I wouldn't. I think they're both valid arguments. The carbon footprint associated with data farms or large servers kept in the deserts is huge. And in a world where, so here's the thing, right? Like, you don't need that level of performance sometimes, but it makes more economic sense for them. So it comes down to the age-old thing that we've known, which is how capitalism works, and where there's economic benefit need not necessarily align with sustainability benefits. I mean, they're correlated, right? If you burn less fuel, there's more money in your pocket. But we've all seen that since it's not a perfect correlation, wherever somebody can exploit an extra $1 at the cost of the environment, they will, and they do. And this is no exception, right? The environmental impact is huge. And in fact, there are studies that go into this. Why are you printing a piece of paper? You can send an email is also a little sketchy. Right? Because somewhere something is running in some server, and some amount of electricity is being consumed. It's just that you don't see it. Part of this is like the adoption of EV vehicles, right? It's not like the energy came from nowhere. It's just that it's not in your house. It's not in your backyard. And there's a lot of that mentality associated with AI/ML, right? It looks like a clean thing, it looks like a more efficient thing, but something somewhere is operating, and it's hard to tell what its carbon footprint really is. And so, for me, that's less than that. The more concerning thing is the behavioral aspect of it, where you don't see the problem, right? Kind of like EVs. So I do think that this is why it's happening, because there is a performance benefit to the ChatGPTs. There are some performance benefits, and if a company is able to adopt it and get that one more user or two more users to click on one more ad or link, it seems to more than make up for the extra cost of the farm, which is built in the wholesale principle and is an entire supply side push. But the ramifications from a sustainability and ecological perspective is not considered as much because the economic benefits more than outweigh it. As with any other technology, this one also paves the way for such things to happen. Your second one was on the moral, this thing, right? Can you just rephrase that part for me one more time?
Please.
Oh, this was the Reddit users and the population.
Yes.
So see, there are machine learning, as AI has always been very privy to the fact that garbage in, garbage out, right? So you bring in data that is biased, you're going to build models that are biased. And people have been working a lot on debiasing models. So it's a very active area of research. It's something people are very aware of, saying, hey, if you're going to learn from racist loan lenders, your model is going to continue to perpetuate that. But being aware of it, you, for the first time, have the opportunity to do something with the algorithms. We're actually working on a lot of algorithms that account and learn about this bias and explicitly correct for it, even if it is not able to get unbiased data. But it is to make the assumption that the data is itself biased, and there's a huge way of correcting for it. What tends to be a piece of the problem is the web component of data. If it's always data that has, if it's biased data, we are aware of it, we know it exists and so on. But the web is a very interesting place, right? It turns out that people in general are substantially meaner on the web, right? So the same political conversation, if 4 or 5 of us were sitting around, it would look very different than if you go on the web and have it. Like, everybody's a troll on the web. So the web as a medium itself has facilitated a lot of toxic data, and perhaps that is getting heightened. But algorithms in general, it's a too hot an area to ignore right now, which is in bias in data and bias in algorithms, and how do I make AI more ethical and fair? So it wouldn't be fair to say that that is not, it would be fair to say that that is a concern, but that's a concern that people are, at least the AI community is investing in heavily in some sense.
Good evening. So when we are building the deep learning model, we have a lot of hyperparameters, right? So hand engineering, that could be a bit difficult. We need to tune each hyperparameters. So instead of that, is there any parallel way we could actually achieve a better output for that, modeling it?
So I'll repeat the question. So when you're doing something like a deep learning network, there are lots of hyperparameters and you're tuning. So first of all, you're not tuning them manually, right? So it's getting tuned in data. Often, if you've got very good starting point for some of these parameters, you don't need to tune them too much, right? So one of the things that help with artificial neural networks or deep learning networks is initial starting values to some extent. But having said that, you can always counter the fact that you have to learn more things or build a more complex model with more data, which is why a deep learning network would be a bad idea if you have very limited data. But if I've got lots of data, I more than compensate for that. But one good thing about much of supervised learning, at least, is we do this technique where we kind of pretend to have not seen some data and then see how well we do on that unseen data, and then kind of surprise the model by saying, see, you got it wrong, or you didn't get it wrong. And so that's kind of like a very clear bottom line. So the beauty of these models is, it's not just that I come up with a fancy model and say, here is my prediction, it's spam. I say it's spam, and I say I'm this % sure, and when I kind of hid it and made it guess, I was right 83% of the times. So we're very statistically minded in the sense of honest in performance. At least the tenets of cross-validation, out-of-sample testing, these are all tenets of good practices. With any project that I do, we do out-of-sample testing, which means we go, no answers for spam or not spam, hide it, try to do the learning and everything, try to go do the predictions on this and say, well, you called it spam and this time you were wrong, and I need to report that. So not only do I give you a tool, but I tell you how good my tool is going to be. And so, ostensibly a deep learning network would perform bad if you give it very limited data and you've got too many hyperparameters. And that would be worse than a very simple regression model or a decision tree.
If I could quickly draw you back to that question on the ethics and the moral dimension of AI/ML. As you know, Isaac Asimov coined the 3 laws of robotics when it was science fiction. It was in the realm of science fiction. And then when the robotics evolved as an industry, they incorporated elements from that. So seeing what you've seen of AI/ML algorithms, if you were quickly asked to draw 3 laws of AI/ML algorithms, the 3 laws, the immutable laws, like the robotics, like Asimov's laws of robotics, what might they be?
That's a hard one.
Is it time to start thinking along these lines, is what I'm asking?
Yeah, I mean, there are frameworks that people are coming up with, right? But I will say one thing, I will say that, I'll tell you at least 2 things. I think it should be compared in some sense. Any AI piece of technology should be compared to the state of the world without it, right? And net, it should have made the world a better place, right? So if it's autonomous driving, I should be able to compare it to human drivers and say that for it to go into production or something, it has to, from a utilitarian perspective at least, have been an improvement. Otherwise, it's problematic. The second thing that I would say is it should not perpetuate the bias. It's hard to say that it will get rid of bias. Because remember, people who were giving loans were only giving it to Caucasian white males. They were not giving it to African Americans. So bias exists both in the data and in human behavior. But if you're going to use AI, it should not accentuate or make it worse. If anything, it should only make it better. That's at least 2 things I can think of. One is from a utilitarian perspective, one is from long term. And I would even go so far as to say, you should say that asymptotically, over time going to infinity, it should debias the entire system, right? Maybe it can't do it tomorrow because it's learning from today's data. It's learning from what's happening, but it can't perpetuate the problem to make it worse. It should asymptotically get rid of some notion of bias.
Nandan, as the session chair, let me exercise my one last question and then we'll close the session. He'll be available for when we're having tea, coffee, so you can ask him more questions. There's a lot of, the questions were largely gloom and doom. Can you give me one good story of how AI can be used in India and probably make our society more inclusive?
So, I can talk about multiple ones. I actually work with multiple government departments. But one of the things that has been very rewarding has been some work that we're doing with the education department. And we are finding that how a lot of learning, both in the private and the public sector, is extensively rote learning. We find that we have a high literacy rate, particularly in the South, but then the actual employability or the usefulness of people is extremely low. And this is not an easy problem to fix, right? Where do you start? Do you start at curriculum? Do you start at teachers? But what a digital platform affords us, and so we've been working with 6,000 government schools which have these things called high-tech labs. It's about 20 to 10 computers each place, and it goes up to 90 lakh students, is that thanks to the digital platform, the world is our oyster in some sense. We're no longer constrained by that one teacher and that one school for that one subject. We have a plethora of content online, right? So, okay, so there's content. So all of this is a success story for digitization. Where did the AI come? No, the content is not the end of the story. How do I figure out which content is needed for which child at which time? That's where the AI and ML come in, right? We do these really nice things where we're able to take all the content on the web And then across these 90 lakh students, and it's 90 lakh is from 6th through 12th, but you take any one class, we're actually able to divide it up, send content. If you have 5 different videos on photosynthesis, who's to say which one is good? We send 1 lakh students one video, we send another 1 lakh students another video, we then send them the same set of exams, see who's scoring better. So in addition to user-defined feedback, like recommendations or rankings or viewership, this platform just allows you to learn so quickly on what is valuable, what is not in terms of content. We're very quickly learning who's copying from whom. We're very quickly learning which questions are stupid questions. Like, there are questions where the question is itself a nonsense question. So how do we learn that? We actually learn that by looking at the distribution of people who've answered it correctly. If some of the students who are known to be better, as well as some of the really bad, then it means they're all guessing. And some distribution of them are getting it right. Whereas if you find that some questions, some people are only answering correct, and these tend to be the better students, you're able to actually learn. So we're learning about questions, we're learning about fraud, we're learning about which content is creating a deeper impact, not just on answering that next question, but laying the foundation for 2 lessons, 3 lessons later. So we have these notions of complementary topics, supplementary topics, prerequisites. We're able to get a rich taxonomical structure and a deeper understanding of what it takes to learn and understand and be better, rather than just rote learnings. And it's been a fairly rewarding experience working with the department. So
I guess I had one last question overruling Jay over here. And this is about the philosophy of science as such. I mean, clearly the issue of pattern recognition and so on, and therefore predictions in science are beginning to overrule, and certainly in my field of material science, in situations where either you don't understand the physics and the chemistry, and AI is doing better in recognizing patterns and therefore producing conclusions, or in situations because the physics and chemistry is so complex and the interactive forces are so strong that you can't possibly write solutions. And so does this mean that we are going away from our philosophies of science, of understanding physics and the chemistry of things, and are we going to replace that totally with AI in the future?
I think that's a great question. It's one that I've thought about a lot as well, because, talking about this, Wired ran an article called The End of Science, about 3 or 4 years back, alluding exactly to this as a fact. What I will attest to, it's a hard question to answer, but what I will attest to is that your observation is bang on, in that, in the past we used to dig the tunnel from 2 sides. You used to dig it from the side of empiricism, which is what do I see, touch, feel, the data-driven kind of an approach, and rationalism, which was not about rationality. Rationalism, the movement itself, was about fundamental principle-based understanding, axiomatic theory, and then you build on axioms, and then you build on logic. It has to do with coherence, not much correspondence, whereas empiricism had to do with correspondence, not necessarily coherence, right? And so most things that we built that were great was a tunnel built from both sides. But what has happened is that one of the digging arms has just become so strong that we're seeing less and less of a need to dig. And we're seeing that even within AI. Even within AI, there was a time where a good AI solution itself had to be dug from both sides. You needed a lot of the human input. You needed a lot of feature engineering, thinking through. And then you needed the brute force, computation. And now you're able to compensate for a little bit of digging on one side with a faster thing on the other side. You're like, no, I don't need that input. I don't need the fundamental principle understanding. I'll learn it. Or I don't even need to learn it explicitly. I'll learn it implicitly. It exists somewhere in a neural network that I can't even extract. But it had to have learned it implicitly for it to work well. I know that for a fact. Otherwise, it's not getting it right? Like, otherwise, I can give it edge conditions and fool it. But no. These guys are learning it very well. So somewhere in that neural network that I can't see, has been a fundamental principle learning in mathematical language. It's just that because I'm not able to see it, it feels like I don't even need to understand it. Correlation over causation, and we can keep moving. So I think your observation is definitely bang on.
With those final words, thank you so much, Dr. Sudarshan and Nandan Saraswam. I think I will hand over to Aditi now, who will take over to the next. Thank you so much.
Thank you.